what I thought we would do now before plunging into chapter 9, which we're about to do, is take a minute and go over one of the problems from the test that did not go well. Because you will indeed have a chance to recoup a low grade on this test by doing well on the final, but that means that you actually have to be able to solve these problems on the final. As you may remember, one of the worked out problems was you have a rock on a string and you're whirling it in a vertical circle. A rock, a string, a vertical circle. The rock's mass was something like 0.2 kilograms and the length of the string was on the order of 8 meters. Now, when you whirl a yo-yo or something on a string around in a vertical circle, it's actually pretty tough to make it go at a constant speed. Why is that? Yeah, the gravitational force keeps wanting to help you out or oppose you. So in fact, it's typically going slower at the top and faster at the bottom. And so we're told here that the top, the speed was something like 10 meters per second, and the bottom, the speed was something like 11.5 meters per second. And basically the problem says, find the tension in the string at these two different instants. Now it's broken out a little bit differently. But this is a problem that you can do if you approach it systematically and start from a fundamental and then really believe it and carry it out. And so what's the fundamental principle if we say, first thing to do is draw a picture, because it didn't have a picture, and a diagram often makes things much clearer. And we can all draw circles, not necessarily very good circles, but we can draw circles, that's okay. And we have these two instants here. Here's our object going around in a circle. And it's probably kind of nice to put in some arrows representing velocity, so we'll say that's the velocity at the top, and so therefore it's the velocity at the bottom, and we figure it's going to be going faster at the bottom. That makes sense. Now to find and we'll even draw the string in here. Well, here's our string, two different times. How do we decide what fundamental principle to use here? What? I'm going to pick one. Okay, so find the tension in the string at the top and at the bottom. That's what we're. So let's pick one instant. We can't pick. Yeah, we're asking for an instantaneous thing, aren't we? And there's only one fundamental principle that has this instantaneous form. That's the momentum principle in its derivative form, isn't it? So presumably we're going to be starting with dp dt equals F net. So then we just do all this stuff that we actually normally do, except you really have to do it. So we're going to pick the top, and we're going to choose a system. What's our system going to be? The rock. And what's in the surroundings? The earth. Is that it? The string. So now we need to draw a force diagram for that instant. So here's the rock. Gravitational force due to the earth goes down, of course. write gravitational force, and then we put Earth in parentheses to show that it's associated with a real object in the surroundings. At the top, what's the direction of the force exerted by the string? Down. The string can't push, can it? So the string, also, I'm just going to draw them the same length. We don't. So we're going to call that the tension force, and we'll write string. And we accounted for everything in our surroundings. So they're in the same direction. So looks like F net is going to be down no matter what. Is that good? What's the direction of dp dt here? Remember, if you're not sure, you can always use this procedure. We take momentum previous, momentum a little bit. So a minute ago, a fraction of a second ago, momentum was like this, and a fraction of a second later, momentum is going to be like that. And so we have P initial, P final, delta P. So it looks like dp dt is down, and that makes sense because dp dt points toward the center of the kissing circle, right? So it would make sense to have dp dt down on your diagram here. Now, so this side says that's the gravitational force plus the tension force. And that's going to be good because we can calculate the gravitational force, right? So that's going to be 0 minus mg0 plus 0. And we want to I just want to show that I know it's negative, so I'm going to write it as a minus the absolute value of, that's all I'm doing here is just showing that I know it's down. What do I do about dp dt, though? Irk. Well, first of all, what about this dp dt perpendicular and parallel thing? dp dt parallel is actually 0 because the magnitude of the momentum here and here is going to be the same. But also we know it's 0 because we know the net force has got to be down. And if the net force is down, that's only F perpendicular. So therefore, we can say dp dt perpendicular actually equals that. So we have the magnitude of dp dt perpendicular is the magnitude of the sum of these two forces. And what's the magnitude of dp dt perpendicular? mv squared over r. V top squared over r is equal to the perpendicular component of the forces, which is that. So we have the absolute value of a minus mg plus a minus tension force. And now we're in pretty good shape, aren't we? Because we know M and V and R and M and G, and all that's left is the tension force. So we can work it out. So let's just put in some numbers. We end up with mv top squared over r. And we have to be careful here with signs. It's going to be minus mg, isn't it? Is equal to the magnitude of the tension force, right? Because we took a absolute value here. So then when we take, so that's going to be equal to mg plus ft. And so we have 0.2 kilograms times, what was it, 10 meters per second squared over 0.8 meters minus 0.2 kilograms times 9.8 newtons per kilogram is the tension force. And with these numbers, this comes out to about 25 newtons, I think, and this is about 1.96 newtons, and so that comes out to be 23 newtons or something like that. Now, what's going to be different at the bottom? So does that make, first of all, before we go on, does that make sense? Now, if you didn't do this, take a minute and think about why you didn't do it. It is actually a somewhat complicated situation, and if you don't go through this analysis carefully, there's about 1 billion errors that can creep in. So what's different at the bottom? Velocity is different. The direction of the forces are different, so we really have to start over at the bottom. Really got to start over at the bottom. So let's draw the force diagram. So the bottom, same system, but here's the rock, same old gravitational force, but now which way is the tension force? Up. And which way is dp dt? Also up. And so which way had the net force better point? Net force had better be up, which means that this tension force has to be greater than the gravitational force, doesn't it? So we have the same, starting from the same principles, we end up with an mv squared over r, except that's mv at the bottom now, is equal to, so we have a minus mg here. So this is really the y component, because y is the perpendicular direction to momentum. So we're writing y components here. So we have a minus mg plus the magnitude of the tension force. And that means that we have an m v squared over r here. In fact, this isn't, yeah, that is what we want. And here we have a plus mg. So this, we don't really need it. Taking y components, so we don't need absolute values, is going to be equal to the tension force. So it looks like the tension force is going to come out to be bigger here, doesn't it? Does that make sense? Why is it bigger? The velocity is bigger, so it has to work harder to turn the momentum. And the gravitational force isn't helping it any. It's definitely making it harder, isn't it? And so this, when we plug this in, this comes out to some number, which is actually bigger now. It's 33 newtons, I think. This is still 1.96, and so this actually comes out to something around 35 newtons, bigger at the bottom. Now you might be going, oh, I don't want to do all that stuff. I can take shortcuts. The problem is it doesn't work very well. I don't know of a way to do this problem except to do it this way, by being careful. And by starting from a fundamental principle. Now there were some hints. It even asked you about the magnitude of dp dt. Okay, so when it does that, that's a hint. You're supposed to think about dp dt. But it's instantaneous. So So go back over this, solve it again yourselves, and think about this if you didn't do well on this problem, because you need to be able to work problems like this. Taking shortcuts isn't going to help. So.